SPIE presents the Advancing the Laser series, honoring 50 years of laser achievements.
Okay, so my name's Mike Dunne. I'm Director of the Central Laser Facility at the Rutherford Appleton Laboratory in the UK, and also coordinator of the HiPER project, which is a European effort to pursue laser fusion energy. This is a consortium of scientists from 10 different countries who have come together, and their goal is to try to realise a long-term dream. You know, can you use a high-power laser to initiate fusion at a level that's sustainable to deliver gigawatt-scale electricity to the grid? The HiPER project is there to try to build on the work going on at the National Ignition Facility in the US, but convert it from a scientific proof of principle into a commercial engineering reality. It's funded both by the European Commission, by the UK government, the Czech government, and by many of the other nations who collaborate in terms of in-kind funding also. It's been going for about 5 years in terms of a 2-year design study. We're now midway through the so-called preparatory construction phase, trying to put together all of the building blocks of what should we do next, what is the technology development track, how do you integrate it all together into a facility. And we're waiting with bated breath for ignition on NIF to see whether we have the scientific proof that will propel us forwards or not. Conceptually, think of it like a car engine. So you have a piston that compresses some fuel. In our case, the fuel is a small ball-bearing sized solid pellet of hydrogen isotopes. They're tritium and deuterium isotopes of hydrogen, which contain respectively 2 and 1 neutrons in the nucleus. The piston compresses that small ball-bearing sized pellet of fuel on top of itself at a scale that, to compare it with, it'd be like compressing a basketball down to the size of a pea. But because you already start off at about 1 millimetre or 2 in diameter, you're compressing it down to a few tens of microns, smaller than the width of a human hair. And if you can do that, and if you can do that in a controlled enough way, you can get extremely high densities, typically 1,000 grams per cc, so that's 100 times the density of lead. And again, if you do it right, you can get very high temperatures, typically 10 million degrees. If you can achieve those conditions, then the atoms will overcome their coulombic repulsion, they'll combine together, and those hydrogen isotopes will form helium, which is an inert gas, and a neutron. The neutron escapes and is used to do nothing more than heat up a blanket which boils water to drive a steam turbine. But if you go back to the first ideas of laser fusion, which actually were generated just 3 days after Ted Mayman's demonstration of the laser itself, just a few miles away at the Lawrence Livermore lab in California, a guy there called John Knuckles came up with the idea of using the laser's ability to concentrate energy in time and space to compress fusion fuel. And then a few years later, in 1972, he published his ideas in Nature and predicted that a laser of about 1 kilojoule in scale would be needed to make this work. Now, I have a kilojoule laser in my lab, and I can tell you that is not enough. And so it turns out that what went wrong in those early assumptions was a lack of understanding, or lack of appreciation perhaps, of some of the instabilities that are inherent in a high-power laser interacting with matter. You can both drive plasma waves, electron waves and ion waves oscillating through the plasma, and you can drive hydrodynamic turbulence in the system. And both of those constrain the problem to a very small region of phase space. And it means that rather than using a kilojoule laser focused down to an incredibly tight spot, you need a much bigger laser, 1,000 times bigger laser, a megajoule laser, focused down to much more relaxed conditions and assemble the fuel using that much larger system. And it's taken 30 years or so to develop the laser technology to get from the few joule to the kilojoule to the megajoule level, which is now, as I say, culminated in this National Ignition Facility. So, and we shall see whether it works or not, but there is high confidence based on the first year's worth of experiments that we're on track for the next year or two. When I talk to students now who are coming into fusion physics or coming into accelerator science and so forth, you can see it in their eyes that great things are happening in front of them and in the lifetime of their PhD and in the lifetime of their postdoc period and so forth. And that just motivates them incredibly. And that motivation is what you need in order to get the innovation, the drive, the pace of change and so forth. And so what I think these large-scale science projects bring is that attractor, the beacon in a particular scientific discipline that attracts people in, many of which then go and work on smaller scale projects or fan out to other applications. But what attracted them there in the first place? Well, it is often the promise of clean energy or developing new medical treatments or maybe just bringing a supernova down into Earth. You know, it's things like that that just spark the imagination of an A-level student or an early degree student and move them into this field rather than some other field. This is a field that is just set to expand enormously over the next 10 years, next 20 years, next 30 years, throughout this century. I mean, just think of the applications in which lasers and photonics are being used already, and you look at the rate of growth and penetration into different fields of science and different areas of society, and that's an incredibly steep curve that is only set to continue to increase. So if somebody wanted to work on a technology that underpins many of the applications that will transform our society over the next few decades, this is the field to be in. You know, high power lasers, photonics, use of advanced optics and so forth. I've no doubt it will continue to transform communications, continue to transform high-speed computing. I hope and believe that it will transform our search for abundant clean energy. I think there's a good chance that it will transform many of the medical and pharmaceutical applications. You know, the list is endless. This is a great field to be in.